Okay, we have a town, or sorry, this is 20A, number 1. A town has 30,000 residents, 12,000 are Democrats, and we're going to take a simple random sample of 1,000 registered voters. We need to match the things in the list. Some of them will be used once, more than once, or even not at all. So the population would be the box, which would be all 30,000 people. Population percentage is 40%. 12 over 30 is 40%. The sample is the draws from the box. The sample size is 1,000. The sample number would be the number of ones among the draws. So we would give every Democrat would be represented in the box by a 1, and everybody else would be a 0. The sample percentage would be the percentage of ones, and the denominator for the percentage is going to be 1,000. Any questions about those? Okay, number 2. A university has 25,000 students, of whom 12,000 are older than 25. The registrar draws a simple random sample of 400 students. Find the expected value in SE for the number of students in the sample who are older than 25. So in my box, we're going to have 10,000 tickets that say 1, and then the remaining 15,000 tickets would say 0. Okay, so we need the average of the box. The average of the box is going to be 10,000 over 25,000, which is, should be 10 over 25 is 2/5, so 0.4. Does everybody understand that? Okay. So the expected value, if we draw 400 times, is going to be 0.4 times 400, which I believe is 160. Okay, so if we randomly pick 400 students at this school, we expect 60 of them to be over 25 years old. Everybody understand that? Okay. And then we need the standard error. So the standard deviation, can we use the trick? Yes, and I'm gonna do a little bit of a shortcut. We obviously don't need to do 1 minus 0. And then I don't want to type in 10,000 over 25,000 and 15,000 over 25,000. So what am I going to do? I could take the zeros out, that's true. But there is an even shorter way, 0.4 and 0.6, right? The average of the box tells me how many, or sorry, what percentage of the tickets are ones. And then the opposite of that is the percentage of tickets for the zeros. So I'm just going to do the square root of 0.4 times 0.6. Now whoa, that's the square root of 6. Now, before I do this in my calculator, what's the number going to be close to? Anytime the number of tickets in the box are close to the same size, then it's going to be 0.5. So this will be a little bit off of 0.5. So the square root of 0.4 times 0.6, and I end up with 0.489. Now what do I do? How do I find the standard error? It's not SD times draws, it's the square root of the draws. So I take 0.489 and I multiply it by the square root of 400, which is 20, and I get 9.8. Now, is that close enough to 10? Yes, and in fact, 10 makes a lot more sense. Why does 10 make more sense? And why are whole numbers important in this case? These are people, right? This isn't a test score or the amount of gasoline in your tank. These are people. So 10 makes a lot more sense. We're just going to say plus or minus 10. So could I have rounded that to 0.5? Yeah. And we're just guessing anyway. So 160 plus or minus 10. Okay. Now, are we really going to go out and do this? No. We already know. Okay. So B, find the expected value in SE for the percentage of students in the sample who are older than 25. What should we do? Well, converting this is really easy. We know that there are 40% 25, all over 25 in the box. Okay. How do I convert 160 into a percentage? Divide it by the number of draws. Okay. Now, when I do this, you're all going to laugh because this really doesn't make any sense to do. Oh, why am I never going to do that again? Because the answer is, oh, it says 0.4. Sorry. There's a glare. So the expected percentage, I'm going to call it the EP, I guess, is 40%. Did I need to do all of that to figure it out? No. If 40% of the people in the box are over 25, if I do any amount of draws, what is my expected percentage? 40%, right? So the expected percentage is exactly the same as the percentage that's already in the box. Now, the tricky thing is, what about the standard error? Okay. How do I do that? Well, there's no... So in here, we have some kind of standard deviation. We figured that's about 1/2, right? So that spit out 10 people. So this 10 represents what? There are lots of ways to describe it. What does this 10 tell us? There's a chance error, meaning you're expected to be off by about 10. What's another way to say it? 68% of all surveys of size 400 will be within 10 people of 160. Okay, so what is this 10 based on? Well, it's based on the SD of the box, and it also takes into account the number of draws. So if we draw 400 times and we are 10 people off, what percentage is that? So 10 divided by 400 is 1/4%. Okay, now watch this. Let's say I had 170 people over 25. I divided that by 400, and I am point... Oh, sorry. Did I do that wrong? Oh, I divided by 4,000. Okay, that makes more sense. It seemed a little small to me. Okay, so 10 divided by 400 is 2.5%. So 10 people represents 2.5% of the draws. Okay, so if I had 170 people in my 400, I end up with 42.5%, which means I'm 2.5 percentage points off. Okay, so my expected value, and we don't really do expected percentage, my expected value in terms of a percentage is 40% plus or minus 2.5%. Have you ever seen something like that before? We expect 40% with an error of 2.5%. What does that remind you of? We've talked about it. It sounds like election polling, right? Ashland is going to get 40% of the vote with an error of 2.5%. Okay? But we haven't quite gotten there yet because in this case, I know what the box is, right? I know what's in the box, and because I know what's in the box, I know what that is supposed to be. And because I know what's in the box, I'm able to calculate the SD, and from the SD, I can calculate the standard error, how far off I expect to be. And when I have a standard error, I can convert that into a percentage, and then I end up with this. Okay? But, once again, this isn't terribly useful. We already know how many kids are over 25. So what's going to happen when I remove the box? So if I go like this, and I put a keyboard up in front of everything to block it, okay, that's the great mystery of statistics. Everything falls apart, right? I don't have this anymore because I don't know what's in there. And I don't have this anymore because I don't know what's in the box, so I don't know the SD. Well, here's the trick. You run out and you talk to a whole bunch of people, and you assume that your percentage is correct. And that gives us this. Right? So let's say I don't know what's in there. I run around and I ask, how many people like, oh, who do we pick on? Parker. How many people like Parker? We talked to 1,000 people. Well, let's say 400. And 40% of the people we talked to like Parker. I know that's a shocker, but it happened. Okay. We just assume that's correct. And I put it in here. Well, how many people don't like Parker? And now I have a box. Where are you confused? So did you understand how we got this originally? Okay, good. So in our original problem, we said if we do 400 draws, we expect most people will be somewhere between 37.5 and 42.5. Right? In fact, 68% of the people who talk to 400 people in the correct manner will land inside this window. Right? Okay. Now, all of this was based on the fact that we had the digital records at the school and we knew exactly how many people there were, right? But if you already know, you're not going to run around and find out. So we are going to draw from a population. We don't know how big it is. We don't know what the people inside there think. So the trick is you go talk to 400 people. Okay, 40% of them like Parker. And we say, that must be correct. That's as good as we can do. So I put that number in the box. Well, if 40% of the people like him, then 60% of the people don't like him. and I put 0.6 in the box. Now, when I use this box, what am I going to end up with? The exact same thing we did before. And we end up with this exact same window. But this window now means something different than it meant before. Originally, this window meant if you make 400 draws, many times, 68% of them will land inside there. Okay? It hasn't happened yet. We know what's in the box. If we were to do this, then 68% of everybody who does this correctly, right, as long as you follow all the simple random sample rules, 68% of you will land inside that window. Make sense? Okay. But what if we don't know what's in the box? What does this now mean? Because it's the exact same calculation, it's the exact same answer, but what does it mean? It does mean we're guessing, right? So I'm guessing and I end up with this window. What does that window represent? It represents what I think Yeah. So what am I looking for here? When I switched it to Parker, what do I really want to know? How many people like Parker? Okay. Well, when I did my survey, I ended up with 40% liked Parker. Is that number correct? I don't know. Right? If I do my sample correctly, if my sample is large enough, then this number should be close. How close? I have a 68% chance that the true value is inside there somewhere. You have just had your first statistic. That is your first statistic right there. Okay? I am 68% sure that the true percentage of people who like Parker is somewhere between 37.5 and 42.5. Okay, now this really freaked people out long time ago because they didn't have computers where they could test this over and over and over and see that it worked. But let me go through it one more time. Okay, if we know what's in the box, I can make a prediction using the expected value, or sorry, the average of the box. I can predict the expected value and the standard error based on the standard deviation of the box. None of that has happened yet. That is a prediction on what will happen when you talk to 400 people at that college. Does everybody understand that? Okay? But that's not statistics. Statistics is, can we figure out what's in the box by only talking to a portion of the box? So what we do is we run out, we talk to 400 people. We do everything correctly. Simple random sample, right? We follow all the rules. We end up with 40% like Parker. Okay? I don't even know how many people are in the box, much less the percentage. So I just go ahead and put 0.4 in the box, which means that the no's must have been 0.6. I use that to calculate the standard deviation, the expected value, and it's not a standard error, it's a chance error. and I say, I think 40% of the people in Emory County like Parker, give or take 2.5 percentage points, which means I am 68% sure that the true percentage of people who like Parker is somewhere between 37.5 and 42.5. Okay, everybody understand that? Now, what do you think about being 68% sure? It's not very good. So what should we do? Let's say I would rather be 90% sure. Then I would change my window. What would happen to the window? It would get a little bit bigger. How? It's just chapter 5, right? It's just your z-score. So we assume it looks like this, right? And this is 0 SDs. If I want to be 90% sure, then I just capture 90% of the people, and that will give me a z-score. And I take that z-score and I multiply it by the SD, or sorry, the standard error, and I can make this window as big or small as I want. For instance, I could say, I am 1% sure that the true number of people who like Parker is somewhere between 39.9% and 40.1%, or something like that. Well, that's not useful, right? How sure do you need to be? And the answer is, you get to pick. Yeah. And that is statistics. It only took us 20 chapters to get there. And I actually told it to you a little bit earlier than the book wants me to, but anyway. Yes. We have built this step by step until we finally get to a point where we can do something useful. Most of the stuff we've done up until now is just prerequisite stuff that you wouldn't understand what we said today if you didn't go back and get all of that. Okay. So C on number 2, the percentage of students in the sample who are older than 25 will be around 40%, give or take 2.5% or so. Okay. Oops. Nope. Nope. 4. 500 draws are made at random with replacement from the box 0001. The number of ones among the draws is exactly equal to the sum of the draws. True or false? True. Because when you sum up zeros, they don't change anything. The expected value for the percentage of ones among the draws is exactly equal to 25%. Yes. Now, the expected sum is more complicated than the expected percentage. Agreed? So why don't we just use expected percentage from now on? Okay, great. Sounds like a good idea. And number 7. Someone plays a dice game 100 times. On each play, he rolls a pair of dice and then advances his token along the line by a number of squares equal to the total number of spots thrown. About how far does he move, give or take how much? So he's rolling a pair of dice. So what's the smallest number he could move on any given? Nope, rolling 2 dice would be 2, and the highest would be 12. And you have to remember our grid. So this is 2, and this is 12. And then those would be 3s, those would be 4s, and so on. Okay. So what is the average of that list? So we have We have a 2, 2 3s, 3 4s, 4 5s, 4, yep. And then the opposite number of 8s, 9s, 10s, 11s, and this would be 12s, and so on. Okay, so the average of the box is going to be 7. And if we play 100 times, 100 times 7 is 700. So in 100 plays, we are expected to move 700 places. Give or take how much? Where's the... Oh, do we have... Somewhere do we have the SD of that box? Where did you get that? Okay. It... And then just doubled it? Oh, okay. So that works. So they... Huh, that's pretty clever. So you could either roll 2 dice 100 times or 1 dice 200 times. That makes way more sense. So the average of this box is 3.5, and the SD of this box is 1.7. Boy, that's way easier than the way I was going to do it. I didn't want to type all those numbers into my calculator. Okay. So I'm now going to do 200 draws. Does everybody understand why that's the case? So my expected value is going to be 3.5 times 200, which is 700. And my standard error is going to be 1.7 times the square root of 200. What is that? So 700 plus or minus 24.